Great. We're happy to have Erik Lindell from Stockholm telling us about abelian cycles and the homology of Torelli group.
All right, thank you. And thanks so much, Jeremy, for inviting me here to give a talk. It's a great honor. So yeah, you've already heard my title. So let me just start by briefly describing what the contents of my talk will be. I wasn't really sure how much background people know about this stuff here. So I'll start by just briefly giving some background on what Torelli groups of surfaces are. And then I'll talk a bit more about what we know about their homology. Or group homology. When I say homology in this talk, it will always be group homology, and it will always be with the rational coefficients, unless I say something else. Yeah. So, and I guess there will be some homology of spaces somewhere, but yeah. All right. So when we have this background, I want to state sort of the main result I want to talk about, which is a result from a paper of mine of the same name as this talk. So if you're interested in more detail and stuff, you can check it out in the archive. And then that should be approximately half of the talk, and then I'll spend the rest talking about how we can prove this theorem. So first I'll go over the two main tools we use, with the first being these abelian cycles from the title of the talk. And then we also need some representation theory. So I'll recall what Schur-Weil duality is, and just and use that to sort of at least sketch the proof of a lemma that we use for the proof of the theorem. So when we have those two tools, the proof is quite short and simple. So unless I go way over time, we should have time to see that proof at the end. All right, and if you have any questions, I guess we have questions at the end, but also if there's anything that seems strange, just stop me and ask. So let me go straight into the background. So starting with the Torelli group, as we said, in this talk, I'll be talking about Torelli groups of surfaces with a boundary. So throughout the talk, SG1 will denote something like this. So a surface of some genus G with a boundary component. And we could do everything in the case of a surface with a marked point instead. And also the results actually sort of, or they do hold for the closed surface case as well, although you need to formulate them a bit differently. But something similar holds, at least I should say. But this gives the more general results, so I'll stick to this case in the talk. So if we have a surface like this, then of course the mapping class group, as I'm sure most of you know, of this surface is defined as the group of isotopy classes of self-homomorphisms of the surface that fix this boundary component pointwise, which I'll denote like that. And then the Torelli group, is simply, and I'll denote the Torelli group by IG1, as you see here, and it's the kernel of the action that we have by the mapping class group on what I'll denote by HZ, which is the first integral homology of the surface. And I think this is the only time I'll take the homology of space in the talk. So, I mean, we can understand a lot of things about mapping class groups by studying this action. So it makes sense to look at the kernel to sort of understand the things we can't see. And I won't really be talking too much about the group structure of the Torelli group. The one thing I want to recall is that for G at least 3, it's finitely generated by so-called bounding pair maps, which I'll try to illustrate for those that don't know about them. So bounding pair maps, and I'll abbreviate those by BPMs through the rest of the talk. Okay, so bounding pair map is something associated to a bounding pair, which is what you see in this picture, just a pair of simple closed curves in the surface that are required to be non-separating and homologous. And then the bounding pair map is what we get by Dane twisting around these two curves in opposite directions in order to get something that acts trivially on homology. So to draw, what this does is, like on some small neighborhood, we sort of twist the surface around the curve like that. So, oh yeah, something like that. All right. So those are the generators and the only elements in the group we will be considering in this talk, but they will appear later. So, okay. So that's all I wanted to say about the group structure. So let's move on to talk about the homology. And we know very little, about homology of Torelli groups, even in the stable range, which, I mean, when we let G be arbitrarily large in comparison to the homological degree, which is also the setting I'll be sticking to. So everything I'll say later on will be for some stable range. But anyway, the one thing we do know in general is that these homology groups have a nice structure. They're more than just rational vector spaces. So the way to see this is to note that this first homology of the surface is equipped with the symplectic form. This is the intersection form of the surface. And since this sort of encodes how curves in the surface intersect, it's preserved by the action of the mapping class group. So this means that the homomorphism that defines this action, which would normally go from gamma G1 to the general linear group, homomorphism, something like that, actually lands in the symplectic group of HZ. And it's a classical result that this is a surjection, which I won't prove, but it's something that we need because this implies that we get a short exact sequence because the Torelli group was the kernel of this homomorphism. So we get a short exact sequence like this. And now just by virtue of this, this means that we get a homomorphism. I'm having trouble with my M's apparently. A homomorphism from the symplectic group to the group of outer automorphisms of the Torelli group. And if this is unfamiliar, the way to do this is just to, if we have something in the symplectic group, we pick a pre-image in the mapping class group, and then we act by conjugation on the left. And if we have two different pre-images, then of course they differ by something in the kernel. So, the conjugations will differ by an inner automorphism, and thereby we get a well-defined outer automorphism. Okay, another point is that on group homology, inner automorphisms become trivial. So this means that we get an actual action when we go to homology. So the homology of the Torelli group is a representation of this arithmetic group SPHZ. And this is the structure that we'll use for the rest of the talk. Okay, so that's nice. But as I said, generally there's very little we know, and we don't really have a good way of working with these homology groups in general, directly, I should say. So the main tool that's been used historically to study these groups is something called the Johnson homomorphism. And I won't really give an actual definition of this homomorphism. So I'll just say that this is homomorphism from the Torelli group to the third exterior power of HZ. This was introduced by Johnson in the early 1980s. And I mean, his definition isn't really difficult, but I don't really know a brief way to describe it. So yeah, but what I do want to say is that on generators, so on these bounding pair maps that we've seen, it's easy to describe what this does. So if we have a bounding pair map F associated to this bounding pair that I've drawn alpha beta, then the way to get tau j of F is to cut the surface along alpha and beta, and then pick the component that doesn't contain the original boundary component, and then taking a subsurface of that with one boundary component of maximal genus, so something like that. And let's call that S. And with that, we have that tau j of F is omega, well denoted by omega S wedge, the common homology class of alpha and beta, where this omega S, I should say, is the symplectic form of this subsurface. Okay, so this formula is also something we'll return to later, so we'll use that in the proof at the end. Okay, but we want to use this to study homology, so we look at the induced maps on group homology. So we get a map which we'll denote by tau n from Hn of Torelli to the nth homology of this abelian group. And since it's abelian, this is just the nth exterior power of the thing we get by tensoring with Q. So we have introduced H to just denote HZ tensor Q. And this that's the notation we'll use for the rest of the, or this is sort of will appear a lot for the rest of the talk. So that's why I used a simpler notation than writing HQ. Okay, so this is the tool we'll use. And for the rest of the talk, I will basically talk about these maps tau n and primarily their image. Before and the next thing I want to say is really sort of what we know about these maps already. But before that, I just want to make a remark that what we can note here, or maybe sorry, I forgot to say. Of course, this the target of this map is also a representation of this symplectic group SPHZ. And the nice thing about these maps, of course, is that they're SPHZ equivariant. Otherwise, they wouldn't be of much use. Okay, so that's something crucial, of course, that we'll use. And the remark I want to make here is that the target here isn't just any representation, it's a very nice representation because it's both finite dimensional and algebraic, by which I mean that it's the restriction of the representation of SPH. Okay, and these are both things we don't know in general about the homology of Torelli. We have no idea, even in the Sable range, if those are finite dimensional in any Sable range, or if they are algebraic as representations. So, I mean, we have a map to a much nicer representation at the point. And this means that to study the image of this map, we can study it as a representation of this larger group SPH instead. And that's nice because, of course, that's just classical representation theory. And to understand the image, it suffices to just know how it decomposes into irreducibles of this group. And the irreducibles, which I also want to recall. So now we'll just recall some representation theory stuff so the coming stuff makes sense. So the irreducible representations of SPH are indexed by partitions, which I'll denote by lambda, and I'll think of a partition as a decreasing sequence of non-negative integers that eventually reaches 0. So it should continue, but only with zeros. We write the lambda for the corresponding representation. And we say that the sum of these, or sort of the number that this is a partition of, so the sum of these integers is the weight of the partition and of the corresponding irreducible, of course. Okay. And two more sort of things I want to say about this is that, or recall, is that if you take the standard representation H and then you take its kth tensor power, then this contains irreducibles, which I'll shortened to irreps of weight at most k. And let's see, right. And also I want to introduce a notation which will return through the talk, that if V is an SPH representation, I'll let V, I don't know if this is good notation, but I'll let V sort of lower k or subscript k in brackets be the subrepresentation generated by all irreducible subreps of weight k. So should think of this as sort of the weight k. I'll probably call this the weight k part or the weight k component or something like that. Okay. So with that sort of detour, let's talk about what we know about these maps tau n. And as I said, I'll be working in, all these results are in some stable range, which I won't specify. The most classical result here is due to Johnson himself, and this is that tau1 is an isomorphism. And this is for, so this is from 1983, I think, from his original work on this stuff. And so, of course, with this, one might hope that all of these maps are isomorphisms. And I mean, I wasn't around back then, but maybe this was something that was conjectured that I actually don't know. But this is not true, because we know that tau n is not surjective already for n equals 2. And we don't know about injectivity. So injectivity would of course be nice, because that would mean that the homology groups are in particular finite dimensional and algebraic in some stable range. So this is perhaps the more interesting question. But they're not isomorphisms, at least. What we do know is what the image is for some small values of n. So the image of tau n is known for n equals 2, which is due to Hein in 97. This is where he proved that tau 2 is not surjective either. For n equals 3, it's also known. And this is due. This was computed partly by Sakasai in 2005, but not entirely completely, but almost. And then an independent calculation of this was done by Coopers and Randall Williams in 2020, where they compute this completely. And I want to say a few words more about this paper by Coopers and Randall Williams. Their paper is not really about Torelli groups of surfaces, but primarily about higher dimensional analogs. And the reason why their methods work there, because there they can actually compute they work with cohomology, but what it is. And the reason their methods work is because there they can show that these homology groups or cohomology groups are actually finite dimensional and algebraic in some stable range. So this means that if we assume that the same is true in the surface case, which, as I said, we don't know, but if we assume it, then their methods are applicable. So if we assume that this is finite dimensional and algebraic, then we can apply their method, and they do this in their paper, of course. Then they can actually show that tau n is injective. So injectivity is equivalent to this being finite dimensional and algebraic. And this is also, I'll just write KRW 2020. And the last result I want to mention before moving on to my own result is that, and this is not really about tau n, but it's about a related map, but this is that there exists surjection from Hn of Torelli to the following direct sum of two irreducibles. And this is due to, I'll write it here, Church and Farb in 2012. So this is, as far as I know, the first result where someone could actually compute, even in a stable range, a quotient of these homology groups for any n. So that sort of tells you how little we actually know about these groups. And this is also their paper, the paper by Church and Farb, is also where I got the ideas for what I'm about to tell you. So they also use the Abelian cycles that we'll see, or similar, or not the same ones, but also Abelian cycles. Okay, so now let's state my result, which is similar to the result of Church and Farb essentially, and it says that if G is at least 3n, then if we take this target of the map and we take its the top weight part, so the 3nth weight component, then this is contained in the image tau n. So everything of top weight is contained in the image. And here I also want to say that this is really a special case of the main result of my paper. So there I have a somewhat more general theorem, which also includes things in lower weight, in particular this. But that's, I don't know, a non-messy way to state that theorem, unfortunately. And it's also more complicated to prove, which is why I want to restrict myself to this here. Okay, so that's the result that I'm going to talk about how to prove for the rest of the talk. I think I've gone about half of the time. Okay, so as I said, unless there are any questions, let me move on to talk about the methods or the tools. The first one are these Abelian cycles. So Abelian cycles are homology classes that we can define in the homology of any group. So here let's just G be a group, and then F1 up to Fn be an n-tuple of commuting elements in this group. And this is what will define a cycle. So such an n-tuple, of course, defines a group homomorphism from Zn to G, simply by mapping the standard generators to these elements, which is why we require them to commute. And we can look at what this induces on homology. Okay. Zn, like the homology of Zn topologically is just the homology of an n-dimensional torus. So this is the top homology, and it's generated by a fundamental class. So we can define the Abelian cycle that's defined by this n-tuple just as the image of the fundamental class. Okay. And we'll denote that homology class by A of F1 up to Fn. All right, so we can do in any group, but of course we're interested in the Torelli group. So the question is, what do we do there? And I've only told you about one kind of element, so it's quite obvious, hopefully, what I'm about to say. But if we take n-tuples of bounding pair maps, and we require that these are associated to disjoint bounding pairs, then those certainly will commute, because I mean if we take representatives, then we can choose the supports to be disjoint. So n-tuples of BPMs of disjoint bounding pairs gives us Abelian cycles in homology of the Torelli group. So this reduces the problem of defining these homology classes to just looking at configurations of bounding pairs on your surface. Okay, and we want to study this map tau n. So the next question is then, of course, if we have such a class in the Torelli homology of the Torelli group, then what is tau n applied to this? Because it's not very useful if we can't calculate that. But this also turns out to be quite easy, and the way to see this is to note that the homology functor is a functor from groups, and I mean we can think of it just as a functor to rational vector spaces, but it's in fact it's a functor to rational coalgebras. So if you use that functoriality, then the map that defined the abelian cycle gives us a commutative diagram, where on the top we just have the map that we already saw. But then we can, on both sides of this, we can apply the n-1 fold co-multiplication, which lands in the nth exterior power of h1. Okay, so why is this helpful? Well, now we can extend this to the right and apply tau n on the top and the nth exterior power of tau 1 on the bottom. And then on the top we land in wedge n wedge 3h, and on the bottom we also land in the same thing. And it's quite easy to show that this that both of these squares commute. So to compute tau n of an abelian cycle, by definition, is computing this composition. But now we can, of course, go the other way around in the diagram as well. So let's do that. If we start with the fundamental class of Zn, then I mean I won't show this, but I mean we understand, of course, the coalgebra structure here well. So this is just mapped to the exterior product of all of the classes of the generators, which is then in turn mapped to the exterior powers or exterior product, sorry, of the classes of f1 up to fn, which is then in turn mapped to well, I mean then we just apply tau 1 factor-wise, which gives us a formula. And now if we, I mean tau 1, should maybe do a new row. So tau 1 of fn. And tau 1 we understand well because we have the form, particularly for bounding pair maps, because we have this formula above for the Johnson homomorphism applied to bounding pair maps. So given a configuration of bounding pairs, then at least up to a sign, of course, we need to specify how we Dane twist, but up to a sign at least, this gives us an explicit element in the image. Okay, so the question is now then, if we have something in the image, then how do we show that it generates this top weight part that we're interested in? So now I want to understand the top weight part of this representation. And in order to do that, I will start by trying to understand the top weight part of just an arbitrary tensor power. And this is where Schur-Weil duality comes into the picture, because this is essentially what this precisely describes for symplectic groups. So if we let k be at least 2, then we have maps from the kth tensor power down to the k-2nd tensor power, given by contracting 2 of the tensor factors using the symplectic form. And then I'll let h bracket k denote the common or the intersection of all of the kernels. So I guess I need to let I and j be different, and then I take the kernels of all of these. And I won't show this, but then it turns out that, and now maybe my notation, the notation I introduced isn't very nice looking, but then h bracket k turns out to be precisely h tensor k and the weight k part of that. So this is precisely the thing we want to study. And Schur-Weil duality describes how this decomposes into reducibles. Okay, and in order to describe that, we first need to note that h bracket k is also, it's not just a representation of the symplectic group, but it's also a representation of the symmetric group, of course, by permuting tensor factors. Because if we have something that contracts to 0, no matter how we contract, that's true even after we permute. So it's a sigma k representation. And this action, the symmetric group action, of course, commutes is what I mean. This commutes with the symplectic action, because that's just diagonal. So this means that we can consider this as a representation of the product of the groups in an unambiguous way. And Schur-Weil duality describes how it decomposes into irreducibles of this product. And here I maybe had left a little bit too much space, but what it says is that Schur-Weil duality, or what Schur-Weil duality says is that this is precisely the direct sum over all partitions of weight k of v lambda tensored with what I'll denote by sigma lambda, where, and maybe I'll move this up a bit. There we go. So where sigma lambda is an irreducible representation of the symmetric group. What it is, if you're not very familiar with representations here, this is not super important to what this is, but it's just it's a sigma k representation. This is the only thing we'll need. Okay, so that's nice. That gives us this decomposition, but I want something more explicit in order to be able to work, say that, okay, this elements or these elements generate the thing we want. So so what you can do is that you can drive the following lemma from Schur-Weil duality. And since I want to work explicitly with some elements, I pick some symplectic basis for H. And then the lemma states that for G at least K, it turns out that H bracket K is cyclic and generated by the tensor A1, tensor A2, tensor, and so on up to AK. Okay, and that means that in particular, if we look at k equals 3n and then we project down to the representation that we're interested in, which was wedge n, wedge 3h, or maybe I should say that for g at least 3n, this is also cyclic, or right, the 3n part is cyclic, and it's generated by the tensor A1 wedge A2 wedge A3 and so on wedge up to A3n minus 2. I'm not sure I have space for this. With this a bit to the left. A3n minus 1 wedge A3n. Okay, so this means that to prove our theorem, we only need to find a class with a homology class which hits this element. Okay, so that's nice. And so let's at least sketch the proof of this lemma. It's not very difficult, but there will be some small details which I'll leave out because they're just sort of a tedious thing or tedious verification. Okay, so here we'll let mu, or what I should say here before I start proving the lemma is that it's clear, of course, that the cyclic representation generated by this tensor is, of course, a sub-representation of H bracket K, because this contracts to 0. So sort of the thing I want to do is just prove that we have the other inclusion as well. So so in order to do that, first we let mu be the transpose of the partition lambda, which just by taking the transpose of the corresponding Young diagram, and then what I want to do is I want to describe the lambda more precisely, or more explicitly. So with this we can define V lambda up to isomorphism as the subrepresentation of the following representations. We take tensor power over all non-negative I, and then we take the mu ith exterior power of H. And since there's only a finite number of non-zero mu i's, this is a finite tensor product, and since mu is also of weight k, this can be viewed as a subrepresentation of H tensor k. And V lambda is then the subrepresentation of this generated by the tensor I. We take the still tensor product over all I at least 1, and then we take A1 wedge A2 and so on up to A mu I. And now you can sort of see where this is coming from. So now we can just say that, okay, if we apply Schur-Weyl duality, then this says that if we just take all of these tensors for all different mu, and then we act by the symmetric group, then we get a generating set for the entire representation. So just a very sort of rough description of that, or a rough generating set we get from Schur-Weyl duality just says that H bracket K is generated by all tensors of the form AI1 tensor AI2 and so on up to AIK. So that's a very rough statement. We don't want to work with all of those, but and this is sort of where I'm sweeping the details under the rug, is that all of these are actually in the representations we want. So the subrepresentation generated by this tensor that we wanted. And proving this is not difficult, but it's sort of just an exercise in applying taking this tensor and then applying the symmetric or the symplectic group in a systematic way in order to get something arbitrary like this. Okay, so that's the lemma. And now we have both a way of constructing homology classes and computing their image, and we have a lemma which says that if we have this single tensor in the image, then we win. So that then we can prove the theorem. And I see I still have, I think, 10 minutes, so maybe I've been speaking a bit too fast, so I'm sorry about that. But at least that gives us time for questions, I guess, if there are any. Okay, so let's finish by giving this short proof of the theorem. Okay, so first we need to define a homology class. So we consider the bounding pair map associated to the following bounding pairs. So you should sort of think of this as a product of n surfaces of genus n, or genus 3, I mean. And then we take, let's just call this F1 up to Fn. And once again, I'm not defining, or I'm not specifying which order I'm twisting in, so this is only well defined up to a sign. Okay, so but let's take that the Abelian cycle associated with those bounding pair maps, and then if we choose the symplectic basis appropriately, by which I mean we sort of do it in the standard way by just, if we start from the left and from the top, we let sort of these the classes of these be A1 and B1, and then we go downwards and to the right. And if we pick that symplectic basis, then the formulas that we've or the first thing is that we need to just apply tau 1 for each of these f's, one by one, and that we know how to do from the formula we saw for the Johnson homomorphism in the beginning. So remember that to compute tau 1 of f1, we just need to sort of consider this subsurface and take its symplectic form, which in this basis is just A1 wedge B1. And then we take the class of the curve that defines F1, or the curves, and that's A2 in this case. And then we just do this for every subsurface separately until we get to A3n minus 2 wedge B3n minus 2 wedge A3n minus 1. And that's of course not the tensor we wanted, but it's close enough. Maybe it's already obvious to you why we can get the tensor we wanted by applying the group action to this, but let me spell it out. So if we let Tij be the element of the symplectic group that's defined on our basis by mapping Bi to Bi plus Aj and mapping Bj to Bj plus Ai, and then all the other basis vectors to themselves, then if we consider, for example, T13 and apply that to our tensor, then I mean that's just I mean it only affects the first factor, this one, and it only affects the B1, and it maps that to B1 plus A3. So if we subtract the tensor we started with, we just get A1 wedge A3 wedge A2, which up to sign is good enough. Maybe I should have added a plus minus here as well, since I didn't specify the signs. And then, I mean, then we can just do the same thing for the next factor, which I guess would be A4 6 and or T4 6, and then so on. So what that course, so writing all that together, that means that if we take the following product, we take from I goes from 1 up to n, and we take T3i minus 2, 3i, and then subtract the identity. Then all of these operators commute. So which order we take for this product doesn't matter. And then we apply that to our tensor, and that corresponds precisely to doing this thing in each factor one at a time. And that gives us precisely, at least up to a sign, A1 wedge A2 wedge A3, and so on, up to A3n minus 2 wedge A3n minus 1 wedge A3n. Okay, and that finishes the proof, and really all I had prepared to say. So I'm sorry if I didn't fill out the time and if I spoke too fast, but yeah. Thank you so much for listening and for inviting me here.
Thanks for the talk. Are there, let's thank the speaker, and then are there questions? Awkward Zoom applause. Yeah, so anyone have questions? Do you think there's gonna, what type of stability do you think actually happens? You kept saying stable range, but
right.
Nothing's actually known, right? Are you
right? Well, I mean, I guess I guess you probably already know the answer to this, but I guess what people hope, I would suppose, is that that we have representation stability, and that these are, injective maps, and like that things should behave as well as they do on tau 1 or on H1. To me, if I'm not mistaken, that seems like sort of one of the motivations, at least, for introducing representation stability originally, right? So, as far as so that's what I would say, maybe, but I have no idea if that's something that's reasonable to expect. So, maybe a bad answer.
Are there other questions?
Yeah, I have a question. Tara, Brendel, and Benson Farb had some abelian cycles. Was it in Torelli group or in the subgroup KG? I'm not sure.
I'm not sure exactly what you're referring to, but I guess if it's in KG, then sorry, go on with your question before I interrupt you.
I thought, I looked at your preprint so that I didn't see their paper. So I guess it was in the second homology of either KG or Torelli group.
Okay.
Or Torelli group, yeah. They compute some non-trivial Abelian cycles there.
Okay, yeah, that's actually not something I've looked at, to be honest, which is strange that I haven't seen it, to be honest. But yeah, yeah. So I don't really have a comment.
Okay.
Honestly, but yeah, if you can send it in the chat, I'd be happy to look at it. Maybe it's something I've seen and I'm not just blanking on what you're referring to.
Yeah, that's let me think of it. Was Berman, Craig, Johnson homomorphism and Abelian cycles in the Torelli group. It was 2007.
Okay.
Matt and Alan.
Okay.
Yeah, I'm sure you can find it easily.
Yeah, probably, yes. Thanks. And thanks for the question.
Are there other?
It wasn't a question, but
right. Okay. Yeah, more of a comment maybe, but thanks for the comment.
Okay.